Okay, so in this lecture, I am going to talk about the very introductory part of nucleosynthesis and the various important topics that we will be covering today are what you can see on the screen. So the first topic that we are going to talk about is the source of energy generation in stars. Now, you see, till now we have discussed about the various dynamical properties of stars. We have talked about their internal structure, how to model them, okay, the state of the stellar material, and various other topics as well. But now what we need is to discuss the issue of the source of this stellar energy. Now let us first start with that of Sun. On the screen you can see here the solar luminosity, which is 4 into 10 to the power 26 watts. Right. Now it is important to note that this flux has not changed in 10 to the power 9 years. And so what does this mean? This means that our sun has radiated approximately 10 to the power 43 joules of energy. And if we use this relation of E is equal to mc square, then what we get is that our sun has lost only a very tiny fraction of its mass, which is of the order of 10 to the power minus 4. Right. So you see, still it has got so much high luminosity, but still over this very large span of years it has lost such a tiny amount of material. Okay, now, so what are the various possibilities of energy generation? Well, the first thing which comes to our mind is the gravitational contraction, right? Now let us get an estimate of the energy which can be released and also the time scale to see whether it is indeed the gravitational contraction which is the source for the energy of stars. Now let us start with considering the sun to be an ideal gas, and then the thermal energy. We know for an ideal gas the thermal energy of a particle is given by 3 by 2 kBT, kB being the Boltzmann constant. So the total thermal energy per unit volume will be given by this number, 3 by 2 kBT into the number of particles per unit volume. Now we have already discussed about the virial theorem, and so I am not going to talk more about it here. You can check my stellar structure lectures. So, but if we just use this basic form of the virial theorem and assume that the stellar material is an ideal gas, then what we get after defining this U, which is the integral over the volume of the thermal energy per unit volume, right? If we define that, then we get that the thermal energy per unit volume is this thing, this particular number. Now, so what we get is that the negative gravitational energy of a star is equal to twice its thermal energy, and this means that the time for which the present thermal energy of the sun can supply its radiation and the time for which the past release of gravitational potential energy could have supplied its present rate of radiation differ by only a factor of 2. Now let us estimate it. Okay, so this is the number, so we will approximately assume, and thus the total release of gravitational potential energy would have been sufficient to provide radiant energy at a rate given by the luminosity of the star for a time, and this is important, this time scale, and using the previous expression over here which we know, then we can get this time scale, and putting in the values we get for the sun this value. You see, for the sun this time scale, which is the, so what time scale is this? Dynamical time scale, and it comes out to be around 3 into 10 to the power minus 7 years. Okay, that is approximately 3 billion years or so. Now, we do have geological data, right? Geological records we have from various fossil fuels and other sources, and these show that the Earth and Moon have existed for over 4 billion years. And what does this mean? This means that the sun has been shining for about the same luminosity during all this period. So this means that gravitational energy can't be the source of stellar energy. Right. Now this number I have written 10 million years of, there is a somewhat different sources they say, so some say it's 10 billion years or some say it's 4 billion years, but the moral of the story is that the gravitational contraction can't be the source for the stellar energy. Now let's talk about the second source possible, which is the chemical reaction. Now again we will consider our sun. So suppose the sun consists entirely of water, or you say hydrogen and oxygen, a very basic example. Then the total number of water molecules in the sun, you see, is just the mass of the sun divided by the molecular weight of water, and it comes out to be 6 into 10 to the power 55 or so. Now the total energy liberated due to formation of the water vapor in the sun, let us estimate it, and it turns out to be of the order of 10 into 10 to the power 37 joule, considering the energy liberated in the formation of one water molecule to be 10 electron volt. Now if we divide this energy of 10 into 10 to the power 37 joule by the solar luminosity, we find that the duration over which the sun would radiate all its energy generated due to formation of water molecule is approximately 10 to the power 4 years, which is much smaller than the 4 billion years, right, age of the sun approximately. So this means that the chemical energy cannot, right, just like the gravitational contraction, it also can't be the source of the stellar energy. So what is left right now? It is nuclear reaction. Now, so you see, the mass of nuclei, let us consider as typical nuclei having several protons and neutrons. Now we do know that the mass of this nuclei does not exactly equal to the mass of its constituents. In fact, it is slightly smaller because of the binding energy of the nucleus. Now since the binding energy of different nuclei can release or absorb energy when nuclei either fuse or they undergo fission, then we get energy. Now let us estimate what energy we get by the simplest possible fusion, which is the fusion of 4 hydrogen nuclei to form a helium-4. nucleus, right? Now here you see I have just written down the atomic masses of the proton and the helium nuclei, and you can easily calculate, check by yourself as well, the mass difference between this comes out to be 0.0285 atomic mass unit, and as a result the energy, which corresponds to an energy of approximately 27 MeV. So what does this mean? This means that approximately 27 MeV of energy is released when 4 protons combine to produce an helium nucleus, and this process in fact do happen in the sun in the pp cycle, which we will talk about in later lecture. Now it is interesting to note that this 27 MeV is approximately 0.7% of mass of the 4 protons. You must remember this number, and I will talk about this percentage again when I will talk about accretion disk later on. Now, so if the sun is assumed to consist entirely of hydrogen, then what will happen? A total of 10 to the power 45 joules of energy can be produced, and you can check using the luminosity. You can do this calculation yourself, and you will see that this amount of energy is sufficient for 100 billion years, and which is much longer than the 4 billion year approximate age of our solar system. So this means that indeed it is the nuclear reaction which is responsible for the stellar energy. Now, regarding this fact, it is important to note that a star shines because of its high internal temperature and not because of nuclear reaction. Okay, so suppose someone asks you, why do the sun shines? Is it because of nuclear reaction? No, it shines because of high temperature. It is in fact the nuclear reactions which replace the energy that is being radiated away, so that the sun, or so that our star does not contract. And when these nuclear fuels are used up, then the star resumes contracting, and then it shines due to the gravitational contraction. Now in this matter, I would like to say that although the gravitational energy is not responsible for the gravitational contraction is not responsible for the stellar energy, but remember that white dwarfs shine because of gravitational energy. That is because of the heat left over from the earlier thermonuclear and gravitational energy generation. Okay, now so let me move to this very interesting binding energy per nucleon versus atomic number chart, which is a very important ingredient in nuclear physics. Now from this chart, what we observe is that if we do the fusion of two smaller nuclei, then the heavier element has got more binding energy per nucleon, which means that more energy will be liberated. Now this thing is true up to 56 iron. So it is energetically favorable using fusion to get nuclei up to 56 iron. And after that, since the binding energy curve decreases, per nucleon decreases, so it becomes energetically unfavorable. Now the question is, how do these elements then are they created? We will talk about it later on, and just to give you a hint, it is basically the neutron capture process which is responsible for these nuclei. Okay, so this brings us to this important topic of nucleosynthesis, which basically deals with the process where new atomic nuclei are created from pre-existing nucleons and nuclei. Okay, so this is basically our topic, nucleosynthesis or nuclear astrophysics. Now, regarding nucleosynthesis, it has got several types. The first being the Big Bang nucleosynthesis, also known as BBN. Now, this occurred within the first 3 minutes of the beginning of the universe and is responsible for much of the abundance of these elements. You see the hydrogen and the helium existing ones. Next is the stellar nucleosynthesis, and this is the one which we will be talking about in this set of lectures. Now, this occurs in the stars during the stellar evolution and is responsible for abundance of elements from carbon to iron. After that, we have explosive nucleosynthesis, which occurs in supernova, and from there, as a result of this supernova explosion, we get lots and lots of neutrons, and which are responsible for the abundance of heavier elements, heavier than basically iron, which I have just talked about. Also, we have this cosmic ray spallation, which occurs in interstellar medium, where the impact with cosmic ray fragments larger atomic species, right? Okay, so in fact the collision with the cosmic rays fragments produce various atomic species. Okay, now this also is responsible for the abundance of these elements which are not created by the stellar nucleosynthesis. Note that apart from these 4 main nucleosynthesis types, we do have 2 more types. Fourth being the neutron star collision, which is the main source for rapid process elements, R process elements, and then the nucleosynthesis inside thick accretion disks, which happen around the black hole. Now, it is important to note that apart from this natural nucleosynthesis or nuclear production processes, there are some artificial nuclear production processes as well on Earth. Well, the first being the radioactive decay, which happens naturally in the Earth, right? Leading to spontaneous fission. Okay, now we do use these techniques as well when in radioactive labs. Okay, so naturally occurring nuclear reactions powered by the radioactive decay give rise to nucleogenic nuclides. Also remember that nuclear reactions do happen when interacting with the cosmic rays inside the Earth. Okay, so now the basic question is, what elements exist? So we are talking about nucleosynthesis, right? And our basic motivation is to answer what nuclei exist and how much the nuclei of each type exist, right? We must remember that apart from explaining the energy generation mechanism in stars, the other goal of nucleosynthesis is to explain the abundance of various elements in the universe. Say for example, I have just shown a sort of typical Venn diagram type. So this is our room where we are sitting. Outside we have our building, our campus, then Earth, the solar system, and the universe. Now, what is the abundance of all the things? Let us start with our room. So the room we are sitting in, including this laptop, including me as a human being, including the chair, including the table, including the fan, the wall and all that, if we consider all these things, then what is the elemental abundance of it? The room. Next, consider the elemental abundance of our entire building. And then our campus. You will see that each time there is a certain change in the elemental abundance. And overall, we will be considering the cosmic elemental abundance. Now, what is that? I'll just come about to it in a second. But before that, to give you an example, now consider a human being. So this is the elemental abundance of a human being. You see, 3.2% nitrogen, approximately 9.5% hydrogen, this much percent of carbon, oxygen. Now, if we consider a cat or a dog, this will somewhat change. Okay. Now the question is, why does a human being has such composition? This is a possible question. But before that, we have to ask that why. So there are two types of questions. If we talk about the abundance, regarding the abundance of elements or atomic composition for a human being, why does a human being consist of this much percentage of elements? This is an important question. And even more important question is regarding the cosmic abundance. That is, why do the certain elements exist in this number only in our universe? Why is it that? Because you see, a human being is formed from those existing elements, right? So this particular composition of a human being is actually affected by the composition, the existing cosmic abundance. So before answering what the question of the composition of a human being, we have to first understand the cosmic abundance, that is the relative proportion of elements in the universe. Now for that, we have to take data from diverse locations on Earth, again solar spectrum, solar wind, the spectra of other heavenly objects, moon, right, even meteorites and all that. And this basically gives us information about the chemical composition of the Earth. So how does this data looks like? Well, it looks like this. Okay, now here I have just shown you the various processes through which these elements are being produced. Now you see certain feature of this plot. The y-axis is particularly the logarithm of the relative atomic abundance, and the x-axis is the atomic mass. The first feature is this. You see, this is somewhat decreasing trend in the log graph. This one is log. Do note that the lithium, beryllium, and boron, they have a very significantly low, you see, abundance. Now, the salient features of this cosmic abundance data. The first thing to note is the very high abundance of hydrogen and helium, which are the most abundant elements in the universe. So, of the total matter, 90% is hydrogen and approximately 10% is helium. Interestingly, you see, less than 1% are heavier elements. The second thing to note is that if we leave out the hydrogen and helium, then we observe that abundances generally increase with mass number up to mass 60. Now this is the neighborhood of 56 iron, 56 or so. Around this mass number there is a broad peak here, you see. The previous plot here, this is a broad number, broad peak or so. Now, I have also demarcated the various regions. So these nuclei are formed by Big Bang nucleosynthesis. This is by stellar nucleosynthesis. These are formed by explosive nucleosynthesis. Now beyond this mass number 60, the abundances decrease, you see. At first the decrease is faster and then it gradually tapers off. So if we come to a conclusion, then the conclusion should be, what we reach is that the origin of hydrogen and helium are perhaps different from the origin of the other heavier elements. Okay. Fine. Now, after discussing about these facts, let me talk about the three very important factors. Now I am not going to show any detailed derivation. We will just have a talk. Okay. Now these three factors are basically responsible for me talking to you right now. Basically responsible for life, existence of life. And not only life, for other elements formation as well. So, now the first thing to note that all the neutrons are locked inside the nuclei. Right now I am not talking about the scenario close to a supernova. I am just talking about a general star. Now note that all the neutrons are locked inside the nuclei. So the only way for stars to make new species of nuclei is through charged particle reactions. Now the most likely process using this charged particle reaction is to combine two protons into a deuteron together with a positron and an electron neutrino. Since protons are the most abundant nuclei by far and have the lowest Coulomb barrier. Okay, now let us make an order of magnitude estimate. I am just going to tell you. Well, suppose the range of nuclear interaction is of the order of 1 Fermi meter, then you can work it out yourself that the Coulomb energy of two protons separated by this distance of 1 Fermi meter is of the order of 1.4 MeV. Now this is equivalent to the thermal energy of a particle at a temperature of 2 into 10 to the power 10 Kelvin. Now remember this number, 10 to the power 10 Kelvin, and this is 3 to 4 orders of magnitude higher in value than the condition existing in the interior of the sun, where we do know that the proton burning is taking place. So how is this happening? Now you see there are two particular reasons why nuclear reaction between protons can start at much lower temperature. The first is that the fraction of particles with thermal energy at temperature T is given by a Maxwell-Boltzmann distribution, and which we know has a very long exponential tail. And it is in fact this exponential tail that ensures that there is a small fraction of particles with kinetic energies much higher than kBt. The second very important reason is that since the collision is a quantum mechanical process, the probability of tunneling is important for any exothermic process such as proton burning. Okay, so these two processes are indeed responsible. Now let me talk about another factor, which is the anisotropy of matter. Now this is normally we do not talk about it, but this is very important. You see, in addition to kinetic energy, a high concentration of particles is also essential to ensure reasonable probability for nuclear reactions to take place. If uniformly distributed, then the proton density in the universe is far too low for fusion to take place in any significant way. Remember that even inside an interstellar gas, the average density is only about 1 particle per cubic centimeter, which is lower than that in a good vacuum chamber on Earth. So, This means that both the high temperature and high density are required to initiate nuclear reaction. And these actually come as a result of gravitational collapse of primordial matter. However, this collapse cannot happen if the material thrown out from the Big Bang is distributed uniformly in space. Okay. Remember that it is only because we are located toward the edge of our galaxy that means ours is a member of a local concentration of galaxies, and if we look beyond our local group, the distribution of galaxies actually turn out to be fairly uniform. So what I want to tell you is that overall we see that the matter is fairly uniform near us. But remember that if the matter is fairly uniform, we cannot have a collapse, which I just talked to you about. Now, the uniformity is also supported by the isotropic distribution of the 3 Kelvin microwave background radiation of photons. So, what is happening? Well, you see, if the density is uniform everywhere, the gravitational force felt by a particle will be the same in every direction, and then there will not be any tendency to coalesce into clusters. Now, in the recent mapping of Cosmic Background Explorer, an intrinsic anisotropy has been observed, and this is of the order of 1 part in 10 to the power 5, this anisotropy. And it has been found that this much anisotropy is adequate for local concentrations of gravity to pull matter together to form planets, stars and galaxies. Okay, so anisotropy, even if it is very small in number, it is important, and it plays a very important role in star formation. Okay, so this brings me to the end of today's lecture.